Hi everybody, my name is Alexey, I'm founder of DeepVerified. I'm gonna talk today about and presenting Conjoined RAG pipeline platform focusing on evaluation. I'm just curious how many people in the audience were able to build RAG platforms? Quite a few. And how many people were able to measure over time the quality of the answers? A little bit less. So that's the focus of today's presentation. The idea of this platform came from the working in regulated environments in fintech. We've seen that financial advisors who have proprietary information, they refuse to upload the information they files into third-party models, and that's basically led to idea to come up with a platform that can be self-hosted and managed within enterprise. And so we'll focus on evaluation piece. So when users submit the question and the answer is, let's say, what's the China's economic outlook for 2026, and system answering 4.6% for the GDP, how we know that it's correct for the self-hosted platform, and that's basically would be focused on for this presentation. And so evaluation has 4 components in giving platform. We're focusing on answer accuracy, retrieval accuracy, that we retrieved correct documents, and latency, how fast platform answers to the question. And the 4th component in observability, so traces that shows us more information in case something goes wrong. Sorry about that. And this is a current platform agentic RAG flow, basically user flow. So basically user submit the question, it produces the query, and system LLM rewrites the query to the more comprehensive question. The next step is retrieving information from the vector database, and LLM would generate the answer. There is validation process in place as well, and if all passes through the validation, we produce the response to the user with the answer to the question. And right now, hopefully it will work. I will do the actual platform demo just to give you an idea how it looks at in work. It will cover the question-answer scoring, query rewrite, and quality performance trends. So, okay. It doesn't, it showed on my computer the platform, but not mirroring there. Sorry about that. Yeah, so yeah, it's running locally on my computer. Basically, the platform, it's a very simple UI that allows you to upload PDF documents with information. It allows you to configure against how many documents the search will work, and it's possible to run the evaluation, trigger evaluation manually or schedule that, and it shows the recent rounds evaluation with performance, the percentage of correct answers and correct retrievers. If something goes down, it kind of shows the percentage lower, and that will allow to look deeper and understand how to debug it. And for giving presentation, I prepared a couple documents from the IMF side that basically covers regional deployment of different regions of the world economic outlooks and world economic outlooks. So it's possible to ask question, what's China's economic outlook in 2026, or what is Africa's economic outlook in 2026, and the platform rewrites the query into more comprehensive version, and LLM gives back the answer. That's basically, I probably will show it later after I'm done with the slides, the platform. So I'll keep going with the slides. That's an evaluation framework. Basically, we have evaluation data set and the RAG pipeline. Again, rewrite, retrieve, generate, validate. Evaluation goes through all those steps, and it works against the expected answer and expected document to measure how well the answer was answered and if we retrieved and worked against the correct document. And it produces metrics, answer accuracy, retrieval accuracy, latency, history, and the trend analysis. And the important piece besides the evaluation is observability. Basically, evaluation tells us what happened, observability tells us why it happened. And for given platform we're using as observability tool, we're using Langsmith for tracing. I'll try to show it as well after I'm done with slides. It kind of gives more information for each stage of pipeline. You can see the latency for each stage and details. So like if we're looking at the right query, it will show you original user question and how it was rewritten. So it just covered the dashboard in at a glance, all the features of the UI that I couldn't show yet. And yeah, so one of the things we were running for different experiments. Sometimes we see that performance is 80% of accuracy, and sometimes it can be accuracy of the answer or accuracy of retrieval. Evaluation actually helps us to identify if it's actually accuracy of the answering the question or we couldn't retrieve correct information from the document. There's performance component as well. Basically, to increase the speed, to lower the latency, we disabled step of rewriting the query, and that's actually lowered the quality of the answers. And all this basically was allowed thanks to evaluation framework. We were relied on measurable and explicit information rather than relying on intuition, and that's the power of having evaluation framework in place. And just the last slide, basically, that's what next for the DeepVerified for this RAG platform is working on large data sets. For this presentation, we had just 5 data sets, basically 5 questions, 5 answers, and 5 references to which document we're retrieving. And as well, the pipeline profiles, in a sense, do we want to rewrite query enabled to disabled? That option increases or decreases the latency, but it as well increases or decreases the quality of the answers. Continuous integration as well for integrating evaluation the same way the unit tests are integrated in the software development. So we're planning to integrate it with continuous integration. The evaluation piece, so if it's something fails or degraded, we see it and we kind of review it and not deploying until it's all accurate 100%. And self-hosted and data sovereign deployments, basically the main idea of this RAG platform. And now I'll try to show the platform. Okay, so here's the basically it's very simple UI where it's possible to upload the document, choose against how many documents platform is working, trigger the evaluation. That's last recent runs of the evaluation, and it's possible to configure the list here, make it longer or shorter. And that's example. Basically, user asked this question about economic outlook in China in 2026, and that was the query rewrite. You can see that LLM rewrote it in more comprehensive question, and that's the answer. Basically, GDP is expected 4.6 growth, a little bit lower than in last year, which was 4.9. As well, the user can see the chunks. Amount of chunks can be configurable as well, and references to actual documents from where it was retrieved. And that's quality trends, basically, that shows accuracy and retrieval accuracy along the time frame, and performance trends, basically how latency changes from run to run of the evaluation. And the last piece is this longsmith observability. So basically, for each question that user asking, we tracking it here, and it shows all the steps of the pipeline. For example, here, for the query rewrite, we can see details. This is original question, and this is a rewritten question by the LLM, and we can see for each step in the pipeline how long it takes. So like if there is sharp increase in time, it's something wrong, we need to take a look at that. Yeah, and last piece is just to show you the data set, simple data set against the evaluation, against which evaluation is working. It's simple JSON file that has recorded the answer, expected question, expected answer, and against which document is supposed to retrieve this information. Yeah, I think that's covered the agility crack.
How is it better than like... hello everyone, thank you for being here. Excited to talk to you today. My name is John Rytel. I'm the CTO and co-founder of Alexey. Alex is a recruiting platform that helps staffing and recruiting agencies as well as large enterprises scale their hiring. So Alex will autonomously source, screen, place, and evaluate candidates. At its core, we have a conversational voice agent that conducts interviews with candidates. And so that's what I want to talk to you about today a bit. Specifically around one of the problems that we needed to solve while building it, which is turn detection. Latency is already somewhat of a solved problem. We just kind of do end-to-end streaming and try to identify bottlenecks. But turn detection is a very interesting problem because it's you have to think about human-AI interaction. It's not purely technical. And more specifically, how do you know when it should start speaking and when it should stop speaking? So to explain how we kind of solved it, let's start with the basics. How do you actually build voice agents? So today there's two ways to build voice agents. One is a voice-to-voice approach, very simple API. You send audio in and then it gets audio out. So if you're familiar with GPT real-time, this is pretty much how that works. It's very easy to stand up. You don't need to worry about the individual providers. But the problem is you don't see what's happening under the hood. That kind of acts as a black box. So the alternative to this is an orchestration architecture. So this is where you manage the transcription model, the LLM model, and the voice model in order to make the voice agent work. And it's pretty much just a state machine. It's a while loop kind of conjoining all these models, and it allows you to have a lot more control over what happens. Gives you visibility into every part of the pipeline, but it means you need to manage a lot more yourself. So you need to manage the latency, you need to manage the turn detection. We decided to go with the orchestration approach just because it gives us a lot more control over the voice agent and the experience that it delivers. This is today, I'd say majority of production voice agents are this type, but over time, 6 months from today, GPT Live just came out, so you might see more voice-to-voice. But let's talk a little bit about turn detection and orchestration models. So what is turn detection? Turn detection is the mechanism that voice agents use to determine when to start and when to stop speaking. When to stop speaking is pretty easy. If you're finished saying what you had to say, you stop talking. If someone interrupts you, you might also stop talking. But figuring out when to start speaking again is the more tricky part. And that pretty much just means you need to be able to detect when a human is done talking. And there are usually two failure cases here. One is you're too optimistic, so you jump in too early, so the agent will interrupt you. So if you ever working with the GPT app or Claude Voice, it might interrupt you. And if that happens repeatedly, that's a really frustrating experience, and just poor user experience. The other failure case is you let too much time pass for the candidate after they stop talking, and that just ends up with awkward silences. The candidate might ask, "Are you there?" And it's just not a good experience either. So the trick is to find a way to be able to get it right every single time. So it's snappy and natural. So the agent waits when it needs to wait and jumps in right when it needs to jump in. And why this is challenging is because there's so many different types of exchanges. You might have exchanges where you go back and forth really quickly. You might have exchanges where you pause for a couple seconds and you expect the other person to not jump in. And so because of this, there's no one kind of size fits all to solve this problem. So how do you decide? How do you kind of figure this out? We started by solving this by thinking about how do we do it? How do humans have conversations? How do we think about when should I start talking now? Should I not? So as humans, we take into account so many different signals. We look at body language, we look at facial expressions, we look at tone, we look at obviously context, eye contact, all of these different things. And that informs us, hey, I should, the person's about to say something or continue talking, I should shut up, versus, hey, it's my turn to speak. But a voice agent only has really two pieces of data. It has the raw audio and it has the transcription. So that's very limited amount of data in order to be able to make that prediction accurately. So the question is, with this limited data, how can you get the most signal possible to accurately and reliably detect when to jump back in? So let's start with the obvious answer, the kind of naive one. Just waiting for silence. So you might think, okay, if the user is silent for, let's say, 2 seconds, jump back in. In this case, the 2 seconds is what we call stop secs. So the amount of time the candidate or the user is quiet for before assuming that they've done talking. And so this works for very simple conversations, but when you really send this to production, it breaks. And in majority of cases, it either results in false positives or false negatives. So either the agent will jump in too quickly or wait too long. And this is because, again, due to the very many different types of exchanges you might have, there is no one value for stop secs that covers all of that. And so you'll have, if you set it up this way, you'll have a lot of false positives, false negatives, and so ultimately this isn't the ideal approach, and doesn't offer the best candidate experience. So what we've thought about when trying to solve this problem is, okay, how do we extract as much signal from this raw audio and transcription in a short amount of time to accurately predict when the user is talking? So this is a pretty simplified diagram of kind of how we thought about it. For any time that Alex or voice agent says anything, we run it through an LLM and we run inference and we try to classify it whether is it expecting a short answer or a long answer. So for example, if the question is like, hey, are you authorized to work in the US? That's a pretty expected short answer, like yes, no. But if it's like, hey, tell me your career history, you might be expecting a longer answer with some pauses in between. So that helps drive, and we make this stop secs dynamic. So for each exchange, the stop secs become different. So in our pipeline, while the candidate is talking, we'll be analyzing the audio. We run the audio through two different models. One is Celero VAD. It's a voice ML model for voice activity detection. And the second is DeepGram's endpointing solution. These are two separate kind of similar models that essentially will send you a signal if they think that the candidate has stopped talking. And then stop secs is an input into both of these models. So what happens when one of these models tell us, hey, we think the candidate stopped talking? At this point in time, we'll optimistically generate the response from our main LLM, and we'll generate the voice so that it's ready to send, but we'll actually gate sending that response back to the client, because if we sent it at this point, it would kind of end up with a lot of false false positives and be interrupting a lot. So simultaneously, we run two things: NLP analysis on it and an LLM to give a confidence level on whether the response is complete or not. So the NLP will just check like, hey, is your response end with a common filler, like give me a minute, or like or things like that. That usually indicate that they're not done talking. And then an LLM as well to say, hey, what is the likelihood that the answer, that this candidate's answer right here is their complete thought to the previous question. And so we use both of these to basically check, hey, to use as the gate before sending the actual audio to back to the candidate. So if either of these say, hey, no, the candidate's not done, we essentially cancel this process, and then we go back to listening to the candidate audio until both the NLP and FastLLM say, hey, this candidate is done saying what they're saying, and then we send the audio back. And so this kind of loop can happen multiple times during a candidate's response. So I might be talking and I might, have a little pause, and the Celero VAD might trigger, but then, the LLM will be like, no, like he didn't completely answer the question. He's probably still going to be talking. And then boom, okay, let's keep on waiting. And so we'll only kind of send the response once we've had one of the models say, the kind of Celero or DeepGram model say, hey, end of turn, and our LLM and NLP are saying, hey, they're also good. And so what this allows us is to have a turn detection mechanism, which is very dynamic based on the context. So depending on what type of conversations you're having, she might actually wait longer or short, or be very snappy depending on what you're talking about. And so after we shipped this, we saw a huge improvement in candidate experience and overall quality, especially in different types of interviews. And short screening calls where it's like quickly back and forth, or like deep technical interviews where candidates are explaining complicated technical concepts. So this is kind of how we solved this problem. So kind of some learnings from this. The first one is, when building, voice agents and even solving these like turn detection problems or building our autonomous agentic systems, well, we always ask ourselves, what would a human do? And what's the expected behavior here? When you want to build natural and human-like agents, that's what you should kind of always, at least a question you should always start at. And then from there, it's, how would a human be better? How can I be better than a human? So ultimately, this kind of starting from here helped us solve the turn detection problem. And we keep on kind of asking ourselves that as we continue building Alex out. Secondly, in many cases, you'll have a very limited amount of data. And so it's important to be creative about how you squeeze as much signal out of that in order to make whatever decision that you're making. What we've learned is many different signals and using them together is often better than any like kind of all-in-one, one-size-fits-all model. At least we found that to be true today. Models are changing really, really quickly, and 3 months down the line, there might be a one turn detection model which is perfect for every language. But that's not the case today. So we're working with the tools that we have, which is fun. And the third one, in our kind of pipeline, we were very optimistic about generating audio, generating responses up until the kind of last irreversible action. So in this case, it was actually sending the audio back to the candidate. And so that was kind of, even though that might have increased cost slightly, it really improved candidate, the user experience and conversation quality a lot. So turn detection was very much just one of the many problems we had to solve in this space. But I thought it was most interesting for the talk today. Other problems with building voice agents are, how do you handle back channeling? How do you handle background speech, tool calling, all of these different things. I think one thing that was kind of most surprising was once we started deploying globally, we learned that, yeah, we learned that every culture and every language has different expectations for how you interact and how you have conversations. And so that we had to kind of fine tune each deployment depending on which language Alex was speaking in. And so it's interesting kind of once you solve this for just English, then like it's not a solved problem for every other language. So how do you make this modular enough and configurable such that you can really deploy it all over the world? So our current version of our voice agent is not exactly what you saw. Very much, the space is changing so fast. It's just kind of one point in time. But it's a really exciting space to be in. Voice agents are changing month over month, maybe even week over week sometimes, with new models, new techniques coming out. So it's a really fun space to be in and stay on top of, and try to build the most human-like conversational voice agent. So if you're interested in working in building voice agents, autonomous systems, and solving problems that help people get jobs, come talk to me afterwards or send me an email. But thank you for your time today.
Hello, guys. We raised from Sequoia a couple months back, like a year ago, to create digital versions of people. And the idea is that we want to make sure that we can represent people really well so that Delphis can talk and sound like them. So we'll be talking about how we are achieving those things. Before that, let me introduce myself. I'm Kaan, AI engineer. Before that, I was at Salesforce AI working on model deployments.
Yeah. Hi, I'm Val, AI engineer, joined Delphi in November, and I'm going to talk to you about the first work I did at Delphi.
Yeah, so to explain what our product first, I'll just go over an example. So we have few customers that are like, we call them immortal. People like Matthew Hussey, Arnold, the big guy, or Jay Shetty. Those kind of people already have an audience, and those people want to talk to those famous people, but those famous people, it's actually really hard to talk to them because they're famous or they're charging a lot of money. So what Delphi is doing is that, hey, Arnold, people want to talk to you. They want to get fitness advice from you. What if we create an AI version of you and you can put a paywall in front of it so that people can take personalized advice from you? So that's what we do. But now we started opening up the free tiers. So normal, like anybody like us could also create a Delphi and they can just send over their Delphi to represent themselves. And for this one, we have an onboarding thing. Onboarding meaning someone, when they open up the Delphi, they are going to be creating a Delphi account. And how we're going to be representing that person involves collecting massive amounts of data about that person. And in our daily life, we know that the data that we're generating is coming from social media generally, or internal, maybe work docs, or like Google Drives, all the things that you have accumulated about yourself. The problem here is that we want to have really low latency. The reason is that when someone onboards, they're putting their social media accounts. Suddenly, we're influenced with a lot of content, right? And when they land onto their profile meaning their own Delphi, they see a picture of themselves. Hi, this is the digital version of me, talk to me. So they are seeing their own Delphi. And generally, we want them to talk to their Delphis to see what it's capable of. But until that, if the training hasn't finished or we are missing a lot of content, and if that person asks a question to their Delphi that is really specific and we are missing out, they lose their confidence immediately with our product. So they churn immediately. So it is about reliability, first of all, and secondly, latency problem. And we've gone through a lot of different styles, and I'm just gonna go through what we've been building. So in the onboarding process, the contents are added, the accounts are added. After even onboarding, they can add more contents. We were doing 5,000 contents a day, but we have scaled up to 100,000 on average per day now. And that is that involves a lot of infrastructure problem and just creative thinking, how we can do things, how we can prioritize specific kind of data and stuff like that. And as you guys could see, 99.8% of the content's actually successful when we do it. You might be thinking, hey, why would it be not even successful? It's just code, right? The reality is that when you're trying to pull data from internet or social media accounts, you can face a lot of challenges. So some of the things include, we're pulling data from YouTube accounts. We're pulling data from Instagram, Twitter, Google Drive, and stuff like that. And there are IP bans that are constantly happening. We need to rotate IPs. We need to download a lot of audio data at the same time, which involves, it's going to create memory problems in your deployments. There's countless amount of problems how we can do that really fast. Right now, we are averaging 4.5 minutes for 90% of the contents getting trained. So we literally have 4.5 minutes to finish 90% of it. And even with that, even if it's 90%, we are making sure we are giving priorities to the accounts that are important, which is like LinkedIn. Because as you guys could imagine, the most amount of data about a person, especially if they're professional career, it's going to be LinkedIn. So things like that. And how we're achieving that is through temporal. So we introduced temporal a couple months back ago, and it is a durable workflow structure. What that means is that there are failovers that get retried. Their state memory management is handled by them, meaning let's say a code executed. Suddenly something crashes. Let's say we were scaling up a lot of containers at the same time. We let's say 50, now suddenly 60, or we're reducing container counts. Then some of the processes might be killed. That means that process might be dying. But if you're using durable workflows, those gonna be saved because they're saving the state of the process on their own servers. So it's get recovered. Yeah, that was one of the examples of what we've done. If I had to go through some of the other things, so let's talk about some kind of audio attribution. So a really classic example of what we would be doing involves, let's say we have YouTube or podcast. Some people like building their own podcast and they like putting that on their Delphi. So with podcast, we're downloading like maybe 50 or 100 hours of podcast. But a Delphi, when we're training the Delphi, it should know at what point the person was talking. Otherwise, we would be attributing the speech to the wrong person. So what we do is that in the onboarding flow, we're getting clips of the person, of them speaking, because it will be used to deep clone their voice. But in addition to that, we will be using that voice to exactly pinpoint which part of the speech was attributed to that person. And if we do that wrong, Delphi is going to be talking about stuff that was not even trained on. So that's like a really big problem. Also, finally, just wanted to really talk about how we're building this, essentially this retrieval system. So it's a temporal knowledge graph, which involves creating nodes, entities, and connecting those entities with each other in terms of relationships. How we do that is that when we extract those data, any kind of data gets normalized. Normalization meaning it's like a JSON file. Any kind of data becomes a JSON file, and those data becomes a tool calling for the agents that building the graph. When they're building the graph, they are aware that a specific content is Twitter and it should be handled that way. But we know that we're associating whatever the entity that's being talked in the content, it gets associated with that entity in the graph so that it gets bigger, and it represents a person much better. I didn't put it there, but we have something called MQS, and which is like knowledge point. We like understanding how dense a person's mind is, meaning if you guys think about it in a vector space, specific content styles or knowledge could be attributed in different part of the vector space. That's kind of similar idea. If a Delphi's knowledge graph has really density in specific area, it's going to get accumulated there. Or some of the topics might have a lot of relationship to each other. An example with that, for me, for example, I'm a software engineer, right? So if there's like an entity that involves software engineering, I'm probably going to have a lot of edges that's close to each other, involving math, maybe, my college classes, my work experience. But also in my Delphi, I talk a lot about my hobbies. Like I like playing soccer. I like going to doing fitness. Those would be a different part of the knowledge graph. But essentially, this is really important because at the retrieval time, we know that when someone's asking about a specific topic, we know that where that conversation is going to be leading towards, because our Delphi agent is going to be pushing the topic in the conversation as well. So that kind of structure, like how are we going to be creating really good simulations of a person, especially when they're talking? That is the biggest problem that we're solving. And this was more of the infra and the how we build the knowledge graph kind of a part. And now Val's going to be talking his own section.
Thank you, boss. But those at work, it's great if we can ingest all your LinkedIn, your YouTube, your Spotify. But is that you? We don't want your Delphi to just be a chatbot. We want it to be your Delphi. And each single Delphi is different. And always, each customer success ticket is basically this question. Doesn't sound like me. And I remember it was my first week at Delphi, and the head of AI came to me and saying, Val, we want to solve that problem. And we want it to be you who solves that problem. And I still remember thinking, how will I solve that? I just joined. How will I solve that? So I came to him saying, okay, do OpenAI have like some kind of paper on it, or Anthropic maybe? His answer was, dude, they have no idea. They have no idea because no one has this problem. ChatGPT is only one chatbot. Anthropic Cloud is only one chatbot. We're one of the few in the world who have this problem. So I zoomed out, and I remembered a story about a book who was written publicly under the name of Robert. And the readers of this book felt like, the writing reminds me someone whose name is J.K. Rowling, who wrote Harry Potter. But they couldn't really prove it. And so they were like, okay, I need to back what I'm saying. I need to prove that the person who wrote this book is the same person who's J.K. Rowling. How they did that is they've applied a technique named stylometry, basically. And by applying it, they've actually proved that, yeah, indeed, it was, she admitted, and she's the one who wrote this book. So how does stylometry works, and how does it apply to our case? Stylometry is basically you ingest all the corpus, all the content that you ever wrote in your life. And we bet that in the way you're writing, there is a fingerprint. There is your fingerprint, your own way of writing. And this fingerprint is hidden in the occurrences of every word you're using. So basically, we do a bag of 50 words, and we say, okay, let's see how often each of one of those 50 words happens. And that will be your fingerprint. That's kind of like your training set. And then we'll take a document and be like, okay, how much does that match? How much does this fingerprint match? And thinking about that, that's the exact same problem that we have at Delphi. I was like, oh, wait. What if I do the same exercise in our own Delphi? So I gathered a bunch of different Delphis. I pulled all the conversation, and I've done the same exercise. I built a fingerprint, and I tried to see if by building a train set and a test set, I could have a good accuracy. We reach bit shy of 70%. Random will be 3%. So we're way above the 3% of randomness. But this is based on real conversation, so it can be based on bias. Some people, like people at Sequoia who have a Delphi, talk of different topics of maybe like sport coaches. So I wanted to push deeper, make the exercise harder. And instead I've pulled a handset of Delphi, and ask the exact same 100 questions. So there is no more bias in the data on the question and the answers. And obviously the score is way lower, exercise is way harder, but we're still way above 3 times the randomness score. And the time we were failing to detect who's who, we're failing actually with the base model, which also gives us an interesting insight. It gives us a score. If your Delphi is mismatched with a base model, it means your Delphi is not trained enough. It means we fail at our job. And this in mind, we've scaled it not only to a score, but also to a test. So that each time we do a release, amazing, it's broken. Each time we do a release, we run a test, and we make sure that your style score for your Delphi, each Delphi has his own score, is always improving. So we always succeed to the question, which is, it must sound like me. That was about Delphi. We are hiring, so if you know a VP engineering, a full stack engineer, or a design engineer, feel free to talk to us. If you want to build your own Delphi, we'll be super happy to offer each one of you their own Delphi. We just released a free tier. And if you have questions, feel free to.